Hello, good afternoon. Today I am here to talk about my paper, A Prototype of Irrigation and Monitoring System for Small Producers, a case study in Ibirité-Mg-Braz, Brazil, by the authors Marcos Guimarães, myself, Thalita Eliezer Guimarães, Lucas Pampoline, Marco Campos, Tatielle Longhini, Elias Freitas, and Pedro Machado. This is the summary of our presentation. Water is one of the most limiting factors in Brazilian agriculture. This activity consumes a significant amount of water, energy, agricultural inputs in addition to degrading watercourses. Although Brazil has a diverse and abundant hydrographic system, some regions suffer from scarcity and disproportionality of water resources. In this sense, for the sustainable development of plantations, monitoring and obtaining data are fundamental. The term employed for the application of these strategies in the agricultural sector is precision agriculture. This way, among various issues, it seeks to observe and implement solutions that allow for the appropriate use of resources, especially water and energy. The region surrounding Federal Institute of Minas Gerais, Ibirité campus, has approximately 80 hectares of vegetable cultivation. This region heavily relies on water sources from the Paraopeba River basin, as it still uses traditional management tools, mostly sprinkler irrigation. Using this as a case study, this paper explores the development and implementation of an initial irrigation and monitoring system tailored for precision agriculture among small-scale producers. The focus is on reducing water and energy consumption to optimize crop productivity, aiming for the operational efficiency and more effective utilization of the available resources. The methodology is divided into three main steps. The first one aims at social environmental analysis, seeking information from the local community involved in vegetable production. The second step involves in applied research, a prototype of an automated vegetable garden aiming to simulate in a controlled environment the production of lettuce, a vegetable commonly produced in the region surrounding the campus area. The third one is planning the system controls logic through a block diagram. For the local social environmental analysis, the first data collected was the method used for irrigation among the way used to pump the water into the system. As shown in this graph, 90% of the farmers use two electrical pumps and only 10% uses gravity, highlighting the high use of the electricity. As for the irrigation, it is well divided between conventional pivot sprinkler irrigation, drip irrigation, and manual irrigation, highlighting no consent of best method and the use of some archaic methods such as manual irrigation. Another data we wanted to collect was the usage of pesticide by the farmers, and for our surprise, 90% of them always used pesticides to combat the proliferation of pests in spite of symptoms appearing or not. Only 10% used when necessary, and only 10% used pesticides with partially organic products and manual weed removal, highlighting how this could be endangering water basins. Now for the applied research, we decided that the best microcontroller for our system would be the ESP32, as it has a low power consumption, it incorporates the main communication interfaces in a single package, such as Wi-Fi, Bluetooth, SPI, and I2C, it has a low cost, and an extensive documentation available online. In this research process, 4 plantation beds were constructed as shown in this layout. 2 control beds, two beds using our control system, both having a micro sprinkler and drip irrigation system. For the online monitoring system, we chose to use IFTTT, which enables automatic interaction between services or devices. In this case, IFTTT acts as a third-party integration system as shown in this layout. The control of the irrigation system is relatively simple, with moisture being the primary variable of interest. Therefore, as shown in this image, initially the microcontroller performs its initialization routine and then reads the sensor signal. If the soil moisture is below 30%, the relay that controls the 24-volt operation is activated, initializing irrigation. After that, a new reading of the sensor is taken, cyclically checking if the soil moisture has reached 80%. Once the value is attained, the current moisture value is transmitted to Google Sheets and the microcontroller is put into a low power state for 10 minutes. After this time, the cycle of sensor reading and moisture assessment is repeated. The result of this paper began with the developed prototype, and, as shown in this image, it was applied to a controlled garden within the IFMG Ibirité campus. In the control systems, we managed to implement a solar panel connected to a battery so it could be set in the middle of the field. The black wires connect our system to the soil moisture sensors and the white one to the solenoid valve. The final results were affected due to planting period not being ideal. In December of 2022 and January of 2023, the Ibirité region experienced a high volume of rainfall. The substantial amount of water hindered the proper functioning of the prototype, as the soil became waterlogged, causing the moisture sensors to malfunction. Productivity was severely impacted, resulting in underdeveloped plants with aesthetically irregular shapes, rendering the vegetables unsuitable for commercialization as shown in this image. To validate the online monitoring proposal, an initial data collection test was conducted. For this purpose, soil moisture was observed in March of 2023 as presented in this screenshot of the collected data and the corresponding graphic of that day. In conclusion, it was realized that the management practices used in vegetable cultivation are not aligned with the concept of sustainability. The use of pesticides and lack of control over water resources contrast with the global trend of sustainable agriculture system. Upon final analysis, this project shows significant potential for social, environmental, and technological impact, offering more sustainable alternatives for the production of small farmers. In further work, we intend to reduce the bed sizes, refine the proposed electronic architecture to better control environmental variables, especially rain and wind. Finally, with the system's improvement, more data will be gathered and we will provide new information for more informed decision making regarding the water and electricity consumption. Thank you.